Hi, let's look at the next question. What solution is better to remove the hardness of water from a given example? So, what's the water hardness first? In yellow on your right, I put it there already, magnesium carbonate and calcium carbonate. So, it's gonna be in an equilibrium. So, between magnesium 2 plus and carbonate and calcium 2 plus and carbonate. So, the more the availability solubility, that will be water hardness. The water hardness, we talk about temporary and permanent, two different things. That's the way we can remove these hard components of the water, but we will not focus on that now. But the whole thing here, the question is how to get rid of this magnesium and calcium. Now we know we can use the ksp um, understanding to remove these magnesium and calcium solubility or solubilized ions. The solid is not a problem because it's deposit into the bottom of the lake, bottom of the flask, wherever it is, right? So that's a common understanding. I will also mention about the soap in this case because that's another thing. But in this case, to answer the question, so let's look at simply, you're going to look at the solubility chart and see each what it will do, right? So now we can see the, yes, the sulfides. The sulfides are um, magnesium and the calcium sulfides are not going to be precipitated, and then the chlorides are not going to be precipitated, and the hydroxides are both magnesium hydroxide and calcium hydroxide both precipitate. So that's the whole point. So therefore the answer has to be both can be precipitated out. So that means C answer in this case, right? So we can prove it just right by writing the ksp for it, right? And also check the solubility chart under hydroxides. See the magnesium and calcium should be low solubility or solid portion of that, right? Okay. The other thing, the other possible question is soap scum. So the soap is actually becomes um, uh, rough and hard and does not make nice soap bubbles because of these precipitation forms, right? Soap is simply this one, long chain fatty acids, right? And um, their calcium salt or the magnesium salt would make basically the soap scum, right? So that will make harder the soap. It will not dissolve. It will not the cleaning job. So the actual functional soap is actually the sodium and the potassium salt of this free fatty acid, right? So the sodium is normally for the normal detergent. The K plus is the body wash. Actually, normally the body wash, the beauty soap and this kind of stuff is K plus because they don't harm the skin, right? Sodium may harm the skin. That's the difference. So when the sodium and potassium is displaced by the calcium or magnesium, the soap is not good. So that's the problem with soap, right? So, okay. So we go to the next question. So the next question is you're given sodium bromide added to a silver bromide equilibrium. So now the saturated solution, silver bromide. So let's start with the KSP stuff. So silver bromide breaks into silver plus and bromide ions, right? So that's the KSP equation. You write that one, and it's at equilibrium. It's saturated. All these things that we know, KSP can be written, and um, it's the ion product. So all these things are true, right? And also the tricky term. Sometimes the question can be mentioning it's barely making precipitate or about to begin the precipitation. All these terms that you can use this normal KSP stuff that we use now, right? That's the idea. Now you're adding sodium bromide, 100% dissolving because like I said, sodium is a first column metal. Remember, first column metals, look at the periodic table and they all dissolve 100%, right? So, and ammoniums and nitrates also. Now, sodium plus and bromide produced from, in this case, let's see what's the effect of, well, sodium is actually spectator, cross it out. Bromide is the common ion in this equilibrium, because cellular plus and the bromide is our ion product, right? Now that's going to be common ion effect. So you increase the bromide, there's no difference. It increases the bromide level of the equilibrium. So increasing ions will shift to the left, because when you increase the ions, it should be consumed. So therefore it shifts left, right? So by shifting left, the solubility of the cellular bromide lowers. So that's the whole point, right? Now, this type of questions are called the column questions. In any competitive exams, you're going to see column questions. So how do you going to do the column questions? You do downward, okay? And we can also put it to the graph just to get the idea what's going on, right? So that's another thing. Actually, they can trick you with the graph, so you may know the theory and then it's hard to describe the graph, right? So the concentration versus time, like I said in the previous one. So the first question I got today is similar, right? So look at the similarity in this one. So if we graph it, concentration versus time, so it should be when it is at equilibrium saturated, and that's cellular plus is a flat level because it's constant for that temperature, for that equilibrium, right? It's at ksp. And also the bromide is also constant, right? So I put in just level almost there, right? And so that's when it is saturated and at equilibrium. Then the only time we can use these, all these ksp laws, ksp expressions, calculations, everything works at 25 degrees normally, right? Now if you increase the bromide because of the sodium, then it spikes up, and then it comes down a little bit, but not to the level of the previous, right? That's a tricky question they can ask you. Now what happens to the silver? It's the other way around. Silver kind of goes down, spikes down, and then comes back and try to come up a little bit, but not to the level of the previous. So therefore overall silver ions go down, but it has a plateau, and the bromide goes up a little bit, right? Now just consider only the silver column. So we saw silver column decrease, silver concentration lower, only B and C is possible. So we don't match with the right side, we just independently finish this column, right? That's the trick of the column questions, okay? So we don't need to go horizontally match. Now look at the bromide separately. We see increased bromide, so that's increased, and increased is the correct answer. Check mark separately. See, the both are correct only on the B. So I don't even match silver to bromide. I independently double checked my answer. My answer is correct that way. That's how you do it, right? So there are other tricks. I'll show you as we go. I think we have another question. Let me see. Um, yes, I do have another question here. So let's see what's that one. Oh, I see. Yes, the KSP explanation can be done using the Le Chatelier principle. That's what actually we did, like I said, 25 degrees. So what you want to do is actually pay attention to this, the at the moment you initiated a change, like injecting some common ion into that, or removal of some ions from it, and that will make the change. And then pay attention to the overall, and also compare the the level of concentration level to the previous equilibrium to the current equilibrium, right? That's how you explain the T1 position. And then also re-establishment, this area is a re-establishment of the new equilibrium. That's how you explain that, right? So two things, you want to consider the LCP, Le Chatelier principle, and then explain it, right? Okay, thank you.